Good morning, good afternoon, and good evening, everyone. Welcome to this webinar. My name is Jim T, and I am an application engineer in MSc Software. In this webinar, I will talk about crack propagation simulation capabilities in MSc Marc. Crack propagation analysis is very important to almost all the engineering industries because it affects the product life, and more importantly, it might cause catastrophic or even fatal accidents. In this webinar, I will talk about the numerical challenges in crack propagation analysis and show you the advantages of MSc Marc in these areas. At the end, I will show you two case studies. When there is a crack in the structure, the first thing we might want to know is probably, will the crack grow? How far and along what direction does it grow? And for different applications, people might be interested in different types of crack propagation analysis. For example, direct crack growth analysis under a damage tolerance, or fatigue crack growth analysis under repeated loadings. For structures with stiffeners, there are also questions for crack bifurcations when the crack goes into the intersections. If we know how the crack grows, of course, we can create our initial mesh to be aligned with the crack growth path. However, usually we don't have this information, so it is very important to update the mesh correctly, especially when the crack growth path is not aligned with the mesh. We can always generate our initial mesh to have the initial crack, but it is not very convenient for what-if studies. For example, if we want to use an initial crack with 2 millimeters long instead of 1 millimeter, then we have to generate another mesh. So providing versatile methods to initiate cracks will save us a lot of modeling time and effort. If the structure has multiple cracks, we need to determine the crack growth speed for different cracks, because usually they are not growing with the same speed. FE packages usually provide some popular options for crack growth criteria, but sometimes people might want to use their own criterion. So it is also important to provide such capability. The good news is that MSc Marc can handle all of these numerical challenges pretty easily. Before I talk about crack propagation capabilities in Marc, I would like to give you a brief introduction of MSc Marc. Actually, Marc is the first commercially available nonlinear FEA tool in the whole world. It has a history of 45 years already. Marc has a lot of advantages in many areas. For example, it provides easy-to-use content capability. In the first animation, we just need to create two content bodies for this analysis. One is for all the beam elements, and the other for the rigid ball. And that's all for the content setup. We don't need to create special content elements and define content stiffness. We don't need to tell Marc where are the areas contact might happen. Marc will model the contact between the beam elements and the ball, as well as self-contact among the beam elements automatically and correctly. There are three different types of crack propagation analysis in Marc, and we will discuss them in more details with the following slides. For direct crack growth, the structure is under some loadings, and the crack will grow if some criterion is reached. For example, in this case, G larger than GC. G here is the energy release rate, and GC is a critical number. And typically for this kind of analysis, we want to know if the crack will grow, what is the crack path, the crack shape, and how far it can go. In Marc, there were 5 out-of-box crack growth criteria. And the user can use user subroutines to implement his own criterion. The critical value in the criterion doesn't have to be a constant value, so that the R-curve behavior can also be modeled. In low cycle fatigue analysis, we apply a number of cycle loadings on the structure, and we grow the crack with some distance after each load cycles. We want to know the crack path, the crack shape, and K or G as a function of crack length. Again, G is the energy release rate, and K is the stress intensity factor. In high cycle fatigue analysis, it is not practical to simulate thousands or even millions of load cycles with simulations. So in this case, we apply a number of representative load cycles to the structure, and we grow the crack at the end of each load cycle. And then we use Paris law to compute the actual fatigue cycles needed to achieve such crack growth. So here is an example. At the beginning of a representative load cycle, the crack length is A1, and it will go to A2 at the end of the load cycle. We can compute the delta K values at A1 and A2 using the deformations of the structure. Then we can use the Paris law, which is shown in the upper right, to calculate the delta N value by integration. If a user wants to use other types of high cycle fatigue equations, such as the Numerical equation, he can implement it with using a user subroutine. We can also use a user subroutine to apply a spectrum load to the structure for high cycle fatigue simulations. When we know the crack should grow, we need to update the mesh after the crack growth. The first method in Marc is released glued contact. Two parts are glued together, and when the crack grows, the corresponding nodes will be released from the glued contact. This method is very convenient for the lamination type of crack growth, and for the two parts that are glued together, the mesh doesn't have to be congruent. In the second method, when the crack grows, we split the mesh at the element faces and edges. Of course, that requires the mesh to be aligned with crack growth path. It is useful for delamination and some special crack growth problems, such as type 1 growth along a specific plane. The last one is the most versatile and powerful one. It combines the adaptive global remeshing with crack growth. When the crack grows, Marc tests all the spaces occupied by the structure and creates the new mesh based on the crack growth increments. Marc will map all the information, such as loadings, element properties, and deformations to the new mesh, and this is done totally automatically. For the new mesh, we can define a global mesh size and define some local mesh refinements based on different criteria. For example, we can create refined mesh near the crack tip, and we can have refined mesh for areas with high stress results. For crack propagation direction, Marc also provides 5 out-of-box methods. And the user can define his own crack growth direction by using a user routine. When there are multiple cracks in the structure, the crack growth speed will be scaled. For direct growth, the scaling is based on the largest energy release rate, and for fatigue growth, the scaling is based on the largest delta K value. And this is an example for multiple cracks. The structure itself is symmetric, but the loading is closer to one flange, so the loading is not symmetric. As you can see from the animation shown in the upper figure, the crack growth speeds for the 2 cracks are different. If we have a 3D crack, we also need to scale the crack growth speed among different crack front nodes. The scaling method is similar to the one for multiple cracks in the previous slide. And this is an example for crack growth with 3D cracks and with multiple cracks. So as we can see from the animation, the cracks are not growing uniformly. In Marc, we don't have to create the initial crack in the initial mesh. This gives us a lot of flexibilities. For example, we can initiate the crack after preloading instead of the start of the simulation. We can also change the crack locations easily for what-if studies. There are 3 different methods available for crack initiation in Marc. Make a cut in the mesh is only available for 2D and shell elements. The second method is split the mesh element edges and faces, and the last one is using global remeshing. The following slides will explain these options in more details. For the first option, cut in the mesh, as you can see from the left figure, a curve is used to cut the mesh. After the cutting, as you can see from the middle figure, some new local elements will be created, and a new crack is added to the mesh, as you can see from the figure on the right-hand side. This shows an example for the second method, split up mesh. Please note that the middle section of the elements are hidden in the left-hand side picture to show you, to give you a clear view. The highlighted element faces will be split up to initiate the cracks, and the figure on the right-hand side shows the initial crack front. And this animation shows how the crack grows. For remeshing method, we can define some surfaces, and Marc will use these surfaces to create a new mesh with initial cracks. These initial cracks are the intersections of these surfaces with the structure. So as you can see from these 2 figures, the figure on the right-hand side are the new mesh with the crack. For structures with stiffeners, Marc will detect the intersections, halt crack growth at the intersections, and create new cracks automatically. This is an example of crack bifurcation in shell structures with stiffeners. As you can see, when the crack passes the intersections, the crack will continue to grow in the panel, and new cracks will be created in the stiffeners. And also, you can see that global remeshing is used to update the mesh. I just talked about the key advantages of Marc in many different areas for crack propagation analysis. Now let's take a look at two case studies. The first case study is the so-called compact tension specimen, or CT specimen. It is a standard ASTM specimen, and ASTM provides theoretical computations equations for J-integral. The J-integral includes an elastic contribution, which is JEL in the equation, and plastic contribution, which is JPL in this equation. Please note that APL in the first equation is the plastic work, and it is a standard output in Marc. For this model, I use 4-node plane strain elements, and this table shows the parameters are used for the model, and the mesh is shown on the right-hand side. As you can see, I'm not using a regular mesh around the crack tip. That gives us a flexibility for generate the mesh. And this curve shows the plastic stress strain curve for this problem. So in this figure, I compared the Marc results with the ASTM calculation results. As you can see, they are almost identical. In the second case study, we are studying the mixture of mode 1 and mode 2 crack growths. The figure on the left-hand side shows the test fixtures, and the figure on the right-hand side shows the specimen. The initial crack, there is an initial crack, and it is in the lower middle of the specimen. The same force P is applied to 2 outside holes on the test fixture, and the applied force direction are opposite. So the angle between the force direction and the center line of the test fixture is called angle phi. When phi is 0, then it is a pure mode 1 growth problem. When phi is 90 degrees, it is a pure mode 2 growth problem. For other angles, it is a mixed mode 1 and mode 2 growth problem. For this problem, we are going to use the CTOD, or crack tip opening displacement, as the crack growth criteria. And the first equation shows you that how we calculate the total CTOD value, delta T. And crack, also as you can see from the second equation, the crack growth angle theta C is also dependent on the local CTOD values. For this model, we are also going to use the 4-node quarter mesh. And if you remember, the CTOD criterion is not an out-of-box option in Marc, so we are going to use a user routine uCrackGrow to implement this CTOD criterion. And also, the crack growth direction in this case is also not a out-of-box option. So we are going to use the same user routine to implement the crack growth direction. The Marc results are compared to 2 sets of data. The first one is also a simulation result. It is a simulation result from another simulation using also CTOD criterion. The second one is the experiment data. Both data are reported in the literature. This slide shows the result for C equal to 0, which is a pure mode 1 problem. As you can see, both simulation results match test data pretty well. And this animation shows how the crack grows and how the mesh is updated with global remeshing. This slide shows the results for C equal to 45 degrees, which is a mixed mode 1 and mode 2 case. Again, the simulation results match the test data pretty well. And this animation shows the corresponding crack growth path. And this slide shows the results for C equal to 90 degrees, which is a pure mode 2 problem. By the way, the figures on the left-hand side shows the force versus crack extension, and the figure on the right-hand side shows the crack growth path. The Marc results are shown in with orange color. The other simulation result is shown with red line, and the experiment data is shown with red dots. So as you can see, Marc results matches the simulation results in the literature, and both of them underestimate the loading compared to the test data. According to the literature, this disagreement is probably due to the lack of friction force in the simulations. And this animation shows how the crack propagates and how the mesh updates with global remeshing. It is a little bit slow, so okay. As we discussed in this webinar, Marc can handle all the different types of numerical challenges shown in this list, including the crack bifurcation, mesh update, especially with global remeshing, crack initiation, and multiple cracks and user routine, user-defined criterion, and crack growth direction. So the conclusion is that Marc is a good tool for crack propagation analysis. Thank you very much for attending the webinar. Now I'm happy to answer any questions you might have.